Hello AP Chemistry and welcome to some practice on 17.3. So we need to find the pH when we add 10 mils of 0.05 molar sodium hydroxide to 40 mils of 0.25 molar benzoic acid. So first we'll start with the reaction. That's always a good place to start. Sodium hydroxide reacts with our benzoic acid, which we'll just symbolize as HA because I don't want to write it out. And that gives us our A-, so our conjugate, plus some water, right? Standard stuff. And now we need to fill in the concentrations like we would for any rice table, right? And we're going to do it in moles because I feel like that's easier. So we have moles of HA, moles of our sodium hydroxide, and initial moles of A-, which would be 0. Then we will subtract off 0.005 moles because NaOH is a strong base and reacts completely, right? Which means we will consume that much HA and subsequently produce that much A-. And now the key thing here is if we look, we have equal moles of HA and A-, which should strike us as a familiar scenario that we've talked about previously, right? Okay, and since HA is a weak acid, we're going to go ahead and write our reaction with water. So HA plus water gives us hydronium and A-. And then, of course, we will write our Ka expression, right, like we always do. And then we need to know our Ka value, which is given to us in our problem. And now we'll go ahead and plug in our values, right? So Ka is equal to hydronium, which is what we're looking for. We don't know what that is. But we do know our A-, and again, we've got to make sure we turn it into molarity because we did our rice table in moles. So we'll go ahead and plug that in. And then what we'll notice, right, like we already said, the concentrations of HA and A- are equal, which means that they cancel, which means that H3O plus is equal to my Ka, right? And if we think about what that means, that's the pH equals pKa scenario that we talked about when we did titrations. Yes, pH equals pKa when HA equals A-, which means that solving for the pH is as simple as taking the negative log of that Ka at this point. Yes? All right, moving on to the next problem. We are going to calculate the pH in a solution formed by adding 10 mils of 0.1 molar acid to 20 mils of 0.1 molar weak base. So we're going to write the reaction for hydrochloric acid and ammonia. This is one you should just know, right? It's going to give us ammonium chloride. Again, we're going to start with a rice table and our initial values. Bearing in mind hydrochloric acid is a strong acid, which means it reacts completely, which means that we will consume all of it, bearing in mind that it is limiting, right? And we will consume that much ammonia and produce that much ammonium. And we'll see that we have the same exact scenario we did previously, right? Where the moles of ammonia equal the moles of ammonium, or we could say that HA is equal to A-, which means that just like in the previous example, we are going to meet the condition where if HA equals A-, that also means that our H3O plus is equal to our Ka, which means that the only reason this one's a little bit different is ammonia is a base, but ammonium is an acid, right? So we could easily write a Ka expression from the point of view of the acid, right? And this is something we referenced back in chapter 16, that the direction we choose to solve the problem just kind of depends on what makes most sense to you, right? We could alternatively solve this using Kb and NH3. We would just have to do an extra step at the end to make sure we went from POH to pH, right? But if we understand what we're doing, this is a very straightforward and simple way to get that job done pretty quickly. You just have to remember that if you were given a Kb, you need to make sure you convert that to a Ka first via Kw, and the Kb for ammonia is 1.8 times 10 to the negative fifth, so we can solve for Ka using Kw, and then again, since NH3 and NH4 plus are equal, our hydronium is equal to our Ka, and we could do negative log of that to get our pH. Yes? All right. Calculate the pH at the equivalence point when 40 mils of this is titrated with that, right? So what does the equivalence point mean again? Right, the equivalence point means the moles of moles of titrant added are equal to moles of analyte originally present, right? So if we go ahead and do our weak acid plus NaOH, right, we are going to get our NaA plus my H2O, right? And so then here, it doesn't even really matter how much we needed to add, right? Because the point is we're at the equivalence point, which means that all of this, so 40 mils of 0.025, all of this has reacted, yes? All of this has been converted to that, yes? So that means that at the equivalence point, I have 0.001 moles of A minus. I need to know what volume it's swimming around in. And we could work that out, but I feel like we can think through that, right? If we have 40 mils of 0.025 molar, and here I have 0.05 molar, which is double the concentration, what volume would I need? Correct, half the volume at double the concentration, which means this is swimming around in 0.06 liters, right? So this is the key thing floating around that's going to affect my pH. Because that's the conjugate base, right? This is the conjugate base of a weak acid, it is basic, yes? It has a tendency to undergo hydrolysis with water and increase the hydroxide ion concentration, right? So let's go ahead and take that A minus, right? And do the next part. So A minus plus water has a tendency to form HA plus hydroxide ion, right? Now, since this is functioning, and sometimes it helps to label this, right? This is functioning as a base in this case, right? We need a Kb value for A minus, which is going to be equal to, right, we're just going to use our Kw and our Ka to figure out our Kb, correct? All right, so let's go ahead and do that real quick. All right, so we've got a Kb, right? And so now let's go ahead and set this up, right? So I know that 1.59 times 10 to the negative 10 is equal to x squared over, all right, and then if we go ahead and solve for x is going to represent this. All right, so if I go ahead and solve for my x is going to be 1.63 times 10 to the negative 6th, and that's the concentration of that, right? And so then I would have to go get my POH and then figure out my pH, which would be 8.21. Yes, does that make sense, right? And that makes sense. Well, we would double check that makes sense because we have a weak acid. We should have a basic pH, which reflects the fact that all of my weak acid has now been converted to its conjugate base counterpart. Yes? All right, and then we've got another one. I don't know, we're gonna have to squish down some of this. All right, so the next part says we have 40 mils of that is titrated with that, right? So same principle. Let's go ahead and get our reaction. And it says that I have, oh, we're doing the equivalence point, yep. So 0.04 times that, which is 0.004 moles of this, right? Which means I would have to add 0.004 moles of that HCl, right? Which, since they're equimolar, that's equal volumes, right? So all of that is converted to that, yes? So now, in my solution, I have 0.004 moles of NH4Cl floating around. Actually, let's just cut that to the part that matters, right? NH4 minus over the total volume of 0.08 liters, right? And again, that chloride, since it's the conjugate from a strong species, has no effect on the pH. We're just worried about that NH4 minus. Now, NH4 minus functions as a weak acid. Okay, so now we're going to take my ammonium and we're going to write down what that does with water, right? So ammonium is a weak acid, which means that that is going to undergo this. It's going to form that plus NH3, right? Deprotonate it, right? It is a proton donor because it is functioning as a weak acid here, which means that I need a Ka, which means that I need to go back to this Kb value, right? And work backwards, and we would find that we end up with 5.56 times 10 to the negative 10th is my Kb, my Ka, which is equal to x squared over 0.004 over 0.08. We would solve for x. So x is equal to this, which is equal to all right, good, makes sense. All right. Okay, so here we have a thinking question where we're going to identify the analyte and titrant for each, right? So analyte and titrant, and not what it is, but just like the type, yes, based on comparisons, right? So let's look at our acid ones, right? So here we have, this one starts with a very low pH, this one starts with a much higher pH, and this one starts with a medium pH, right, and looks funny, right? So our analytes here, right, so we would say that this one is the strong acid, right? This one is the weak acid, and this one is a polyprotic acid, right? Because of their initial pHs, right, and those initial pHs and their respective equivalence points, right? This equivalence point is higher than this equivalence point, right? And the titrant then in this case would be where it ends, right? So that would be a strong base. Titrants tend to, they have to be strong species, right? Because the titrant is what has to react fully. Yes, it needs to react completely such that it is always limiting up until we pass the equivalence point. So it doesn't make sense for it to be a weak species, right? So here again, it would be a strong base, and here it would be a strong base, right? Now in this figure number 2, obviously my analyte has to be a strong base, and this would be a strong acid, yes? And we can see that because if we compare these first two, they have a pH approximately the same for where their equivalence point is, yes? Okay, so this question's asking us or telling us that we have equal volumes of two acids are titrated with the same base, right? Equal volumes. Note that it says nothing about their respective concentrations, and then it asks us to interpret which is the more concentrated acid, right? More concentrated acid means that there is more total acid, moles of acid present, right? More moles of acid present. Now, what are we going to look for on our graph to tell us how many moles of HA are present? Right, we are going to be looking at the respective volumes required to reach the equivalence point. Yes, the respective volume to reach the equivalence point. The red acid required more of the 0.1 molar NaOH, which means it had more acid present. Yes, obviously the assumption here, right, is that, well, actually there's only one equivalence point, so yeah, they're all monoprotic. So it required more of that acid, right? So this one is the answer to A, right? More concentrated. All right, now we might be tempted to go ahead and look at the pH, right? To talk about concentration, but without more information, that would be hard to tell because, we don't know their Ka values, and look, this follow-up question asks us about Ka. Now, this does give us some information, right? The fact that the red one has a lower pH means that initially, before we do anything to it, there is more hydronium ion present, right? More hydronium ion present, which could reflect more concentration, right? But it could also, in this case, right, reflect the larger Ka, where Ka, again, larger Ka means more of it dissociates, right? Which is what this initial pH gives us information about, right? In addition, we could also look at our equivalence points, right? This one happens at a lower pH, right? And if it happens at a lower pH, that means it's a stronger acid, yes? The higher that pH goes, the weaker the acid is, yes? Weaker the acid, the stronger its conjugate, yes? All of those things are things we could consider. We could also then, if that's the equivalence point, right, we could also analyze, the half equivalence points, right? And the respective approximate pKa's, right, would be another route we could go. So all of those are things we could discuss with in terms of interpreting the Ka values. Good? All right, next up, the graph shows the titration curves for two monoprotic acids, right? Which curve is a strong acid? So here we're looking for the hallmark features of a strong acid titration, right? And I feel like that is clearly B, right? We don't have, we just have what is a straight line here, right? No initial inflection points. We have a lower initial pH and a longer rise accompanying our equivalence point. what is the pH at the equivalence point? So typically what we do is we will look at where in between those inflection points, right, we'll go halfway and call that the equivalence point. So the pH at the equivalence point here is about 7, right? And for the blue one, same thing, right? We'll look for inflection, right? And halfway, right? And we would say, I don't know what that is, like, what, 8.5? So looking at the last question, we have 40 mils of each acid was titrated with 0.1 molar base, right? So we're using the same concentration of base for each. We have the same volume of each, but if one of these requires more volume of NaOH, the one that requires more volume must have had more initial moles of acid present. Yes, does that make sense? If it required more moles of base, that sample must have had more moles of acid initially present. Yes? All right. Thank you for listening. Be good. I will see you soon. And coming up,